Hello and welcome. It's my pleasure today to be speaking to Dr. Bharat Reddy, Senior Scientist at Rectify Pharmaceuticals. It's particularly wonderful to be speaking to Dr. Bharat Reddy because he has published the first use of commercial HexAuFoil grids. Dr. Reddy, could you introduce yourself a little bit and say a little bit about Rectify Pharmaceuticals?
Yes, thank you for having me. As you mentioned, my name is Bharat Reddy, and at Rectify Pharmaceuticals, we develop positive function modulators, which are essentially just small molecules that restore or enhance membrane protein function. Our company utilizes a proprietary platform for rapid discovery of these PFMs. And our goal is to come up with not only first-in-class, but also best-in-class small molecule therapies to address various membrane protein dysfunction in both rare and common diseases. And some of our targets include liver, cardiorenal, metabolic, and neurodegenerative diseases.
Can you tell me a little bit? So obviously that's very exciting. What development pipeline? Could you tell me a little bit about how you're leveraging cryo-EM in that pipeline?
Yes, cryo-EM is one of the main techniques we use to determine on-target binding and target specificity. So that's one of the main ways we use it. Additionally, we use it in our iterative drug design pipeline. First, we usually do a high throughput screening initially, but once we get our high throughput screen hits, we use cryo-EM as a way to validate those hits and then make those hits better. In other words, help them bind to the protein better, help them dial out some potential toxicity issues if we have them. So it gives us a very detailed view of how these drugs interact with our targets.
Okay, that's very interesting. Thank you. And could you talk a little bit about what your cryo-EM setup is for those kinds of studies at Rectify? What's it look like in the lab?
Yes, we are a very small company, and due to that, we do not have our own cryo-EM set up directly. So what I do is we use a combination of two things. Either I do stuff in-house with local neighboring universities, or we use a CRO. And so with our in-house, I actually purify the proteins, I make the grids myself, but then we use like a local university. Being in the Boston area, there's quite a few. So between MIT, Harvard, and UMass Medical, we're able to leverage it. On the other hand, so I do a lot of method development in-house. However, if we figure something out, we often transfer it to a CRO. So if we need to do multiple structures, they have the throughput and the manpower to do it more efficiently.
That's very interesting. And I think that's a very efficient way to do things like that. I think quite a lot of smaller companies like yourself use that kind of option.
Yeah, I mean, it's very difficult to justify a $7 million microscope with a $2 million room when your company only has a few dozen employees.
Very true. Very true. Obviously, we're here today to talk about your brand new preprint describing structural studies of the bile salt export pump, which we're very excited at Quantifoil is the first publication using data from commercial HexAuFoil grids. Before I ask in more detail about the cryo-EM, could you tell us a little bit more about the protein and why it's of interest to you and Rectify?
Yes. BSEP, also known as ABCB11, is a member of the ABC supertransporter family, or transporter superfamily, and it functions to transport bile salts across the liver canicular membranes. Loss of BSEP function results in impaired bile acid flow, and this is a characteristic of many diseases such as PFIC2, BRIC2, and ICP.
Okay, that's very interesting. And how are you using cryo-EM in this project? What do the structural studies really give you that enhances what you can understand about the BSEP?
What is actually very interesting is we're actually able to determine So the class of proteins that we're currently developing are a class of proteins, the class of molecules we're developing are called correctors. And it's very interesting with cryo-EM, we can easily determine what compound or what drug is actually a corrector or a potential inhibitor. How it binds to BSEP gives us a lot of insights into how this drug is actually doing what we think it's doing, and allows us to predetermine which ones we should focus on and spend time and try to develop versus ones that we should just stop. Even though it binds on target, it might not be worthy of moving forward due to potential toxicity effects. So one of the problems with a lot of drugs is, a characteristic of BSEP is it actually is a very promiscuous binder. It binds a lot of drugs and can be inhibited by a lot of drugs. And so one of the tests that a lot of drug companies have to do is determine if a drug binds to BSEP. And what we're actually able to do is see which way it's going. Now, it isn't completely definitive, but it gives us good insights of which way we want to go with a particular drug, whether we want to move forward or not.
Okay, that's very helpful. Thank you. Now, so obviously, the thing we're excited about is the use of HexAuFoils and structure solution. It sounds like this was it's been an ongoing structure project, and I guess you've used other grids, other Quantifoil grids. And I was just interested. So the publication you've made obviously uses the HexAuFoil grids, and I was interested in what difference that made and why you chose to use them.
Actually, interestingly enough, the original format of the publication, or the original version, actually used ultrafoil grids. But as you know, you guys came out with HexAuFoils within the last year, and I was very interested in using them. And so the resolution difference between going HexAuFoil going from ultrafoils to HexAuFoil was almost a half-angstrom improvement in resolution. And there are multiple reasons why, which we can talk later or we can talk now, it's up to you, that we saw this huge increase in resolution.
Okay, well, we can talk through that, because actually I was going to ask you a little bit about it. So we might as well start at the beginning. Did you change the way you did sample prep, and was the way they sat on the grids compared to ultrafoil different? Did you see, I don't know, a higher concentration or a better number of views, less preferred orientation or anything like that?
Yeah, we definitely saw a lack of orientation preference. So that was a great advantage. I would say the sample prep between the two actually is different in the sense that, again, we're comparing ultrafoils to HexAuFoils. The main difference is the blotting time, the blotting force and blotting time. In our experience, we basically followed the recommendations that you had in your publication for the HexAuFoils, but long story short, we had to use a harder blotting force for a longer period of time.
That's, yeah, as you say. And did you also glow discharge them longer than ultrafoil, or about the same?
Much longer. So we followed your protocols, and with ultrafoils, we usually do 30 seconds glow discharge. Granted, every machine is different, but for our particular machine, we went from 30 seconds to 90 seconds.
Thank you. That's just to give people an insight. Somebody's actually solved the structure. The kind of what we're recommending does help. And what software were you using? Was it EPU or Serial EM?
It depends where we collected. So this is actually one of the great advantages of HexAuFoil is, and a potential disadvantage as well, is you have to have a microscope that has the latest version of EPU. If you try running HexAuFoils on the older EPU versions, in other words, they haven't done the Windows 10 software upgrade, then you cannot pick out individual holes. It just doesn't work. So you first have to have a microscope. The other thing is, which I'll also mention, is I'm not a big fan of using microscopes such as the Glacios or the Arctica because you cannot get a beam tight enough to actually image all the holes. You end up having to skip half the holes if you start using one of those microscopes. And so I did all this work exclusively on Titan Creosis with either a K3 or we used a Falcon 4.
Yeah, and that is indeed, yeah, they do work best if you've got fringe-free imaging so that you can have the beam just over one hole. I should say, just for people listening, you can use them with a Glacios, but you're quite correct. You can, you're wasting 7 holes essentially for every one you collect. Still, because there are a large number of holes on a HexAuFoil, you still probably end up with more holes available, but it's not as ideal as using with fridge-free. Sorry. Okay, and
well, I would like to also add one of the main advantages once you do have either CRLM or EPU set up to use it, your throughput in imaging is substantially higher. So on average, we were able to get on EPU. I mean, obviously this varies on what radius you choose for beam shifting, but we get about 800 an hour on EPU and about 1,000 images an hour on serial EM.
Fantastic, that's great to hear. And we have more recently been advising people to be careful with eccentric height and also around image shift calibration. I guess that was your experience as well, that setting up.
Oh, that is something that you have to be overly cautious on. In other words, you need to make sure you have the best image calibration as you possibly can, because any slight errors are propagated, especially as you go to larger and larger radius of beam shifts, that it could potentially put half your images out of the hole. Yeah. So you have to be very, very careful with the image calibrations.
Yeah, but we have been saying to people it's kind of like a stitch in time saves 9, that famous thing that you have to take a little bit of time, but as you said, once you've got it set up, because they are so consistent and stable, you can collect very quickly. Yeah, that's great to hear that they are working the way we'd like to see them work. And what about data processing and model building? Did you notice any differences? You've said there's this extra half-angstrom. Did you notice anything different about the data processing? I guess just taking a step back.
Yeah, let's start with motion correction. I think that's the most important thing. The main thing is oftentimes we see less than 1 angstrom total motion.
Yeah.
So it is, each image that we collect has almost no motion, which almost begs to differ. If people had these grids back when film existed, could they have gotten atomic structures? Yeah. I don't know. It seems very possible. But that being said, one thing I should add is when we're collecting these data, we're collecting at 215 magnification. And so one thing, well, we might talk about this later, but one thing is like that could be part of the explanation of why we're getting higher resolution structures is we're already starting at a very high magnification in the DQE. If you go any lower magnification, I'm not a big fan of 165 or 130 because you start getting too much gold in your image. Yeah. And so I rather just, go to high 215, almost encapsulates the entire whole. And I think that's a better magnification to start at.
Yeah, that's an interesting viewpoint. We've been suggesting 165 for collection, but yeah, certainly different people have different tolerances for gold, I think. Yeah.
I would say so going back to just motion correction and all this other stuff is the other thing is ice thickness. The one thing that I love about these HexAuFoils is within a HexAuFoil, the ice is fairly consistent in thickness. Or not a HexAuFoil, I should say in a hexagon, since you don't have squares anymore, you have hexagons. Yeah. In each hexagon, the ice thickness is very consistent. across the hexagon. So it's very convenient to just, once you find a hexagon that has the correct ice thickness that you're going for, then you can actually just image that whole hexagon without any issues.
Yeah.
Not too much variation. And then the other aspect is, since these holes are much smaller, the variation within the hole of ice thickness is pretty much non-existent. If you do like a 1.2, 1.3, like ultrafoil, or even a 2.1 or 2.2, the problem is the center of the hole is oftentimes way too thin versus the edge of the hole. And so you get these vast gradients of protein across the whole hole. But at least with these HexAuFoils, it's much more consistent across the entire hole. Granted, these holes are much smaller, but the consistency is quite nice.
Yeah, thank you. Yeah, thank you for saying that. And yeah, we do have some illustrations of that show that, yeah, we can get down to very small variation actually in the ice thickness, especially compared with earlier grids. And yeah, as I keep saying to a lot of people, I think it is the consistency that makes things easier. And then when you work through into actually reconstructions and model building, some people have said that they're seeing what they feel are less noisy maps. I don't know if you also thought that as well.
Yes, since a lot of our projects are membrane protein projects, we usually have either a detergent or a nanodisc, or detergent micelle or a nanodisc. And one thing is, in traditional using ultrafoils, it is very noisy in that area. However, by using these HexAuFoils, we are actually able to see much clearer density of lipids sometimes, of detergents, of small molecules within these noisy regions that were much harder to see otherwise. And I don't know how much of that has to do with just having almost no motion and motion correction, or some other characteristics.
Yeah, I mean, one of the things we are actually, and people should look out because that will be an upcoming webinar, is we're actually doing some work, starting to do some work internally, looking to try and see what the difference is, whether it's the motion or consistency that's giving us those kinds of results. Do you think you'll continue to use the grids in the future? And do you think there are particular types of proteins or projects that will benefit from using them?
Yeah, almost exclusively all our membrane protein projects have switched over to HexAuFoil. We are either in the process of enabling them for HexAuFoil or already have them enabled.
Fantastic. I love to hear that. And what's next for BSEP, actually? I mean, I was talking to you before we started this interview and saying that I thought the publication, people should go out and read it. And though you can't see it now, when we launch this, we will put a nice clear link during the talk to the publication. And I thought some of the stuff you were looking at with those different mutations was really interesting, and being able to group them by different effects on the stability of the protein. And what are you planning on doing next with the protein?
So we've just announced that we have developed some PFMs for these BSEP, and a sister program with ABCB4. So BSEP, another name for BSEP is ABCB11. But we've also worked using HexAuFoils as well on ABCB4, which we haven't published yet. And we've developed some PFMs that we would like to see go into the clinic one day.
Wow, that's very exciting to hear.
So we're actually able to see in the 2.x resolution these PFMs bound to the target, and which gives us great confidence in their function.
Fantastic. That's lovely to hear. I think we'll wrap up the interview now. Just want to say thank you so much for your time, and we're going to be really eagerly looking out for these next developments. It's going to be very exciting. Thank you very much for speaking to us today.
Oh, no problem. I'm glad to share my experience.